So, is there a talk?
Oh, sure.
Yeah, here we go.
Right.
All right, folks, we're going to start up again, shift gears a little bit. I am old enough to have started programming in 8080 assembler, made my way through C and C++, live in C# mostly, and if you twist my arm, I'll admit that I do JavaScript as well, although mostly reluctantly. So I am most interested to hear Samir talk to us about Go.
Hello, I'm Samir Ajmani. I manage the Go programming language team at Google. I didn't start off as a manager on the team. I joined as an individual contributor, a programmer, about 4 years ago, and then slowly took on management duties. At the time, I was developing the libraries and infrastructure needed to use Go inside Google. So the language is stabilized at that point. We really wanted to make it useful for building production systems internally. My background at Google is in distributed systems, so Go I found to be remarkably interesting for building those kinds of systems. And then just recently, this February, I took over management of the whole team. So I've been trying to wrap my head around the broader problems and challenges around making languages useful for the great diversity of things people are trying to do. I'm going to talk to you today primarily about server programming. That is sort of where Go came from, and hopefully get you interested enough to program your next server in Go. Here's the outline for the talk. We'll talk a bit about what Go is, where it came from, the history, and who's using it today, both inside and outside in Google. I'll spend a few slides comparing Go to other languages, just to give you a sense of where it falls in the space. And I'm going to spend the bulk of the talk presenting code. This is a very code-heavy talk. I'm not going to be writing the code, but I'll walk you through it and show you some example executions. And I'm going to be presenting a server, a web front end with sort of an interesting distributed search backend, and that's going to demonstrate some of Go's concurrency primitives in an interesting way. And I'll conclude by giving you tips for how you can get started with Go in your organization. So what is Go? Well, according to golang.org, it's an open source programming language that makes it easy to build simple, reliable, and efficient software. It looks great on the label, right? What you need to know here is, first of all, it's open source and free. Second of all, simplicity was a goal from day one, and everyone says simplicity. I'm going to try and make the case through both the code examples and discussing what is in the language and what's not in the language that we really worked hard to try and achieve something new here. In terms of reliability and efficiency, Go is a safe language, and it's designed to produce fast programs. It also compiles fast, which is great for your developers. And so I'm hoping to show you throughout this talk how we achieve the goal stated here. Go's design began back in 2007. As legend has it, Robert Griesemer, Rob Pike, and Ken Thompson were sitting around waiting for a large C++ program to compile. And so they had some time to think about everything that was wrong with the programming languages Google was using at the time. They were joined shortly thereafter by Ian Lance Taylor and Russ Cox. Go became open source in 2009 and has since built a very active open source community. The language stabilized in 2012. That's when we called it Go 1. And since then, both the language and the standard libraries are backwards compatible. So programs you wrote in 2012 compile and run today. And we're going to be releasing Go 1.7 this August. So why Go in the first place? Why were Ken and Robert and Rob sitting around griping over the languages? What problems did they foresee? What were they trying to solve? Fundamentally, Go is an answer to problems of scale at Google. Here's a picture of Google Data Center. So obviously Google comes from a background of massive programs that run on lots of machines, and also massive teams that are trying to get big jobs done. So there are really two problems of scale. The first one is system scale. Designing programs to scale to thousands or even millions of machines. It's common at Google that jobs are running on thousands of machines and are communicating typically via RPC. Furthermore, disparate jobs need to coordinate and interact with others in the system. What this means is that there's a lot going on at once in our software. And the fundamental way that we help our users get a grasp on that is by building in support for concurrency into Go and making it very easy to employ that, to structure your program in a way to make sense of this madness and to deal with things that are happening concurrently, things that deal with failures and things that are taking different amounts of time to execute. I'll go deep into this in the example and show you the kind of power you get from building this into the language. The second kind of problem is engineering scale. Supporting large teams, building large code bases, iterating quickly. From 5 years ago, these are old numbers, we had 5,000 developers across 40 offices, lots of changes to the code base, lots of turnover in the code base, lots of test cases executing. We build out of a single giant code tree, and we run all the affected tests with any important change. And so we needed a language and a build and test and deployment model that scaled with this, that helped us deal with the problems that we're dealing with in Java and C++, and in particular, as they scaled on this axis as well. So Go is trying to solve both of these problems. Actually, before I go on, one thing that's interesting here is that while we were trying to solve Google's problems, both of these problems have turned out to be not just our problems. Not just other enterprises, but people deploying software to cloud are dealing with these kinds of large-scale systems and very interactive concurrent systems. And it's not just true at large scale, it's even true locally, that if you're dealing with a mobile device, there's a lot going on at once. There's a lot happening in the background, as well as user interactions, as well as interacting with other services and notifications. So this notion of concurrency and giving the programmer a handle on that is critically important to a lot of kind of software. And similarly, engineering scale, well, this is bread and butter. This, we're all dealing with a lot of things changing, and we need languages that scale with that. So who uses Go at Google? Hundreds of projects, thousands of programmers. We have millions of lines of Go code, and it's growing quite rapidly. I'll go through a few public examples. One is Flywheel, which is a speedy proxy for Chrome. This is particularly important for mobile devices that are bandwidth constrained, say in developing countries that have limited networking. So this is doing on-the-fly compression and serving of web pages to mobile devices. Next is dl.google.com. This is going to serve all of your Chrome and Android and Earth downloads. Vitess, this is a big one. This was actually one of our oldest production systems written in Go. It's YouTube's MySQL database balancer. And this has been serving all of YouTube's database traffic since 2011. So Go has been, I won't just say it's production ready now, it's been production ready for a while, and we use it in a big way at Google. There's a couple more on here. Lingo, we moved all of our logs analysis from Sawzall to Go. So Sawzall was an older Google-developed language specific to logs analysis, and Go is a general-purpose language that gives people who are writing logs analysis more power and more ability to do proper unit testing and things like that. And so Go succeeded in a completely different domain as well. So while our target here is network servers, Go is a general-purpose language. You can use it for apps, you can use it for tools. Docker is one of our big external adopters, and they're largely building command line tools and frameworks like that. So let's look at some other external adopters. I'm not going to read this list, but just give you a sense of the flavor here. We've got hundreds, if not thousands, of external companies using Go. A lot of them are startups. Startups have the distinct advantage of not having a large pile of legacy code to integrate with, so they tend to try new languages quickly. But we are seeing adoption in enterprises as well. Again, if you're developing tools or servers, standalone binaries that can communicate with the rest of your system, that's a good opportunity to try a new language. And so we've seen a number of companies trying it out. And our community is quite enthusiastic. This bus at the bottom is from CoreOS, and that giant figure on its side is the Go Gopher, which is the language mascot. So they painted a bus with our Gopher. They like it that much. The GopherCon conference in Denver sold out the last few years with 2,500 attendees per year. So, and now there's, I think, a dozen such GopherCons running around the world. It's a lot of fun. So let's talk about how Go is similar and different from the languages you know already. This slide is from a talk by Brad Fitzpatrick back in 2014. He titled it Go 90% perfect 100% of the time. He's on the Go team. He's tried a variety of languages. He developed LiveJournal and then came to Google. On these two axes are sort of what I realize now are traditional debates between developer productivity and program performance. So on the y-axis, as you go up, you get languages that tend to be more fun, that tend to support more rapid prototyping. You get the dynamic languages, Ruby, Python, Perl, and JavaScript. On the x-axis, high on the x-axis, you find C and C++. These are what people still turn to get the most performance out of their programs, to get the most closest to the metal and control that at the lowest level. And Java, you can see, is sort of making a trade-off in this space. It's fairly efficient, and it provides a lot more safety and developer support than C and C++ do. And JavaScript as well, you can see, is sort of coming across on the efficiency axis. It's been quite optimized. Our claim is that Go finds a new point in this space, probably comparable in performance to Java, maybe a little better once you start employing some concurrency. But we believe it's a lot higher on that developer productivity axis. And let's talk a little bit about why. So I'm going to compare Go to Java for a few slides. So first of all, Go has a lot in common with Java. If you know Java or other Java languages like it, Go will be very familiar. So that's going to lower your learning curve. We actually think Go is pretty easy to learn if you're coming from a C or Java or related background. So Go is in the C family. It's an imperative procedural programming language, curly brace complete. Statically typed, compiled. It's a garbage collected language. We have, over the last few years, optimized our garbage collection for low latency. Our focus has been on servers, but we are also now doing more and more work to optimize for throughput workloads as well. Go is memory safe. You can have nil references, but nil references in runtime and bounds checks are checked at runtime. Variables are initialized to 0. This is all bread and butter. You know this coming from these other languages. In terms of programming model, Go will give you methods and interfaces and runtime type information, so you can do type assertions and reflection. So let's talk about differences. Go differs from Java. This is again comparing to Java, not the other languages, in several ways. On the sort of fast, efficient for computers axis, Go programs compile to machine code. There's no VM, and this means that we can optimize for the architecture. I moved my bullets around here. We also produce statically linked binaries, which means you can compile your program, copy it to the machine you want, and run it. You're not pushing a whole bunch of dependencies around. This also means you can cross-compile for the destination architecture, so you can build a Windows binary from your Mac and copy it over there and run it. This makes deployment a breeze. Go also gives you control at the language level over a memory layout in your structures and your arrays. This means that your program spends less time chasing pointers. You have the ability to control the allocation patterns in your program if you're in indirections. This gives you an axis of control that you don't get in some other languages. In terms of developer productivity, Go really has a simple and concise syntax, and you'll see that in the code examples. It is lighter on the page than a lot of the statically compiled languages. It's going to have more of the look and feel of your dynamic language. Again, you get the statically linked binaries, which simplifies deployment. And in terms of language features, you get lexical closures, function values, built-in strings and maps, and so on, and that built-in concurrency, which we'll spend some time on later. Now, I claimed that Go is simpler. Now, it can't be simpler if we just took an existing language like Java and added stuff. That would be Java++. That's Scala, right? We have to leave things out or take things away if we really think that this is a smaller, simpler experience for the user. Because fundamentally, if you have to think about all these choices, all these different things you could be doing, that's paralyzing, right? So by actually constraining the language, you get something that allows you to be more productive. So Go has no classes and no inheritance. That doesn't mean you don't have, you can have types that have methods and interfaces, but it's not quite the same as having classes and inheritance. There's no constructors. There's no final modifier. You have compile time constants, but no final on your data types. There's no exceptions. I'll show you how we do error handling in Go. There's no annotations. There's no aspect-oriented programming in that sense. And finally, there's no user-defined generics. And this tends to be a big sticking point for people considering Go. They think, how could you possibly have a language in 2016 that doesn't have generics? After all, Java added generics in Java 1.4 back in 2004. So clearly they figured out it must be a good idea. Why haven't you? And this has been an active area of debate in the Go community for several years and within the Go team. What's interesting is all that time, during all that debate, we've gone ahead and built big production software quite successfully. And the pinch of not having generics has not actually been nearly as significant as you might expect. I'll show you in the examples how we built something interesting. And part of what helps here is we have a few built-in generic data types built into the language, so that takes care of a lot of common cases. And for the rest of it, well, you'll see. So why leave out these features? Why make the language smaller? And the answer is clarity is critical. Go is optimized for the code reader over the code writer. This is because you spend a lot more time maintaining your software than you do producing it. So when reading your code, it should be clear what the program will do. So it should be relatively straightforward also how to implement certain behaviors in your program. Idioms and conventions are good. They help comprehension. And so when you're writing a code, it should be obvious what you should do to make the program do what you want, right? Sometimes this means you're going to write out a loop instead of invoking some obscure library function, and that's okay. The don't repeat yourself mantra certainly has value. There's good reasons to reuse code, obviously, but don't dry out. It can be overdone, and it can force you to have to learn, say, a bunch of helper libraries where really you wanted to write 3 lines in line and move on with your life. So there are some interesting philosophical differences between Go's approach and what's come before. If you want to find out more, there's 2 great talks by Rob Pike on these, Less is Exponentially More, and Language Design in the Service of Software Engineering. I strongly recommend those talks. All right, so let's get to the code. So again, Go looks familiar. Here's hello world. You start with Go programs begin execution in package main, func main. This is all very familiar, right? Package statement at the top, import statement, we import the package fumped. That's our package for formatting strings. And in the main function, it takes no arguments. We're calling the println function from the fumped package, printing out hello world. Go source code is Unicode. So we've got our nice Chinese hello world there. So then I just clicked the run button that compiled and executed my program on my laptop. So I said Go is for servers, so here's a server. This is a web server that is going to serve that hello world text on the endpoint hello. In our main function, the first thing we're going to do is register a handler for the hello endpoint, calling the handle function from the HTTP package. And we're going to say that we're going to handle that endpoint using the handle hello function, which is defined here below. The next thing main is going to do is going to print out the host and port it's serving on, and then we're going to block in listen and serve and tell it which host and port to listen on. And that function shouldn't return unless something goes wrong. If we're unable to bind the port, it'll return, and we'll log fatal. We'll dump our stack traces out so we can analyze the error. Handle hello, the signature is now determined by what handle func needed. It takes 2 parameters, a response writer, that's the object that's going to let us write the response back to the user, and the HTTP request. This star here, this is a pointer. So Go has pointers, they are safe. And so they think of them like object references in Java. We're going to print out our URL, and then we're going to write that hello world string directly to this HTTP response writer. Now you may have noticed that in Go, the type declarations come after the variable names. This is, if you remember old languages like Pascal, this is familiar. For those of you who grew up on Java and C, this look a little strange, but you get used to it very quickly. And there's good reasons for this. You'll see in some of the type declarations later. The other thing you'll notice is there's sort of varying capitalization throughout. So Go has only 2 kinds of visibility. We don't have public, private, protected, so on, and so forth. There's just exported and unexported. Exported means things outside your package can see it. Unexported means they can't, right? So it's the equivalent of package level visibility versus public. And so capital means exported, and lowercase means not. So you don't need any more keywords. You just name it this way. And this isn't just convention. This is enforced by the compiler. And it works surprisingly well. So let's run our little server. We're serving on this URL. Open that up. There's our hello world. Great. And you can see here's that log message we printed with our URL. All right, so here's the example we're going to work with through the rest of the talk. This is a fake Google search front end. So the handler here is going to call a function that will fake out some Google search results for us and then render those results to the handler in a few different formats. And when we get to that function that renders the Google search results, we'll talk a lot about concurrency and how we'd actually fetch results and deal with them from a distributed set of backends. So here this looks just like our hello server except for the endpoint is search. And our handle search function has a contract that it needs a query parameter queue, and optionally you can specify an output format, which is JSON or pretty JSON. So let's run that server. And if we just click that first link, we're going to get an error message. We're missing that query parameter. Click that second link. Here we get some rendered search results. We'll see these again a little later. We get a web result for the query Golang, which is the Go programming language homepage. We get an image result, the Go Gopher, and a video result for another great talk, Concurrency is Not Parallelism, also Rob Pike. And you get a little text at the end saying we got 3 results in 200 some odd milliseconds. That's a fake time. If I reload a few times, the time will change, and you'll see how that's happening later. So I'm going to walk through some Go code and Go syntax here. This is to help you guys get familiar with it. First thing we're going to do is log our URL and then check for that query parameter. Here we're calling a method on a request called form value. We're asking for the query parameter q and saving it in this local variable query. This colon equal syntax is declaring and initializing a variable in one step. So we don't have to state the type here. The type of query is determined by the static type of the right-hand side. So the right-hand side here is this method call. And you can see it declared below here. In package HTTP, we have a type request. And we have a method, which is a function on request. This is the receiver, called form value that takes a string key and returns a string. This means that query is going to be a string, right? So this is the tiniest bit of type inference. There's no Milner type inference here. This is just local, saving you having to declare the type when you're declaring local variables. But it turns out to save you a lot of typing. If the query is empty, then we're going to render this missing the queue parameter error to the user, just calling this helper function to write that response to user with the HTTP status code. Great. This is all straightforward. So now we're going to fetch the search results. Here we're going to use a package I'll show you later. The package is called Google. Here what you're seeing is an import path for a package in Go. The first part of this path, golang.org/x/talks, is the identifier for the repository. And how long that is depends on the repository. This roughly maps to a GitHub repository. The next is just the path within the repo, and finally you get the package name. We have tools that can automate fetching these packages to your local workspace. So given a Go program, we can automatically fetch all of your dependencies and install them for you. Returning back to our handler, we're going to run the Google search. We're also going to time how long it takes. So we're going to produce 2 things. Well, first we're going to run Google search on the query, and it's going to give us 2 return values. So Go, you can have multiple return values, and a very common kind of last return value is an error. So here we get the results. We have an error. Results is a slice. A slice is, think of it like a growable array or a vector. Slice of search results, and I'll show you that type later. And the error is an interface value. Interfaces in Go are interesting. All an interface is specifying is a set of methods that a type must implement. Okay? So it's really just a constraint on what you can do with that type. But you do have runtime type iteration. You can then do type assertions to find out more about the underlying type and the value. So right now, since we've just got an error out of this call, all we can do is call this error method to get a human readable string. And that's all we're doing here. If we get an error, if the error value is not nil, we're just going to print that string to the user and report an internal server error. But say we wanted to learn more. We wanted to find out, okay, what more can I learn from this error in terms of structured information? Was there a timeout or something else? You'd use type assertion to find out more about that, either using other interfaces or if you know the concrete type you're looking for. So now that we have the search results, we're going to do a bit of we're going to put them in a little structure so that we can integrate with the rendering a little bit more easily. So we're going to declare a little inline type. This is a type declared locally inside our function body. It's just a struct called response that has 2 fields, the slice of results and the elapsed time, which is a duration. And then we're going to declare a value called resp, which is that response. And here we're just specifying a little struct literal with the results and elapsed time we got from our call. And so this composite literal syntax is very, very handy. You may remember it from C. You can specify it using positional struct fields, but you can also specify results, colon, to do the separate fields, and the rest will be 0. The same syntax works for maps and slices. And this is, again, something you would see in a dynamic language, right? You're used to seeing this in, say, JavaScript, but it turns out to be just as useful in statically compiled languages, and is particularly useful when you're building things like protocol buffers, right? Messages to send over the wire. You can specify it as a struct literal. You can really see what the message is rather than constructing it with call after call. So this ability to sort of lay out your memory, frankly, or lay out a value structurally, turns out to make your program quite a bit more comprehensible. Right. Finally, we're going to render our search results. Remember we had this output query parameter. We're going to request that with this rec.form value. We're going to switch on that value. You remember that is going to give us a string. So we're switching here on a string. Each case is a string. We've got a case for JSON, a case for pretty JSON, and a default. In the JSON case, we're going to use the encoder from the JSON package and encode the response. Now, a response is what? It's a struct with two things, a slice of results and an elapsed time, okay? And so when we go back to our server, I think I have a run on the next slide. There we go. So let's run our server and open up our URL and see our JSON result. So here's that same results we saw for the web, but in JSON. And it's kind of hard to read. It's all packed together. But you can see there's a results and there's a title, something. So let's render our pretty JSON instead. And that was just another case there. All right, there we go. This makes more sense, if that'll ever disappear. I don't know why it doesn't want to make the title bar disappear. But we get our slicer results, the title URL. So what the Go JSON package did is it took that Go structure, that Go value, and simply mapped it with a reflection over to a JSON value. And of course, you can do the reverse on decoding side. So you have a bridge now from your static typed space in Go to your dynamic space and your wire space in JSON. So it makes that integration very, very smooth. So I showed you we have regular JSON, we have an indented form, which takes a little bit more information, and then we have this response template to render our HTML. So Go has its own templating package. There are third-party Go packages for standard ones like Django and so on. Each of these cases is taking the response and it's doing two things. It's setting this error, if there's an error, and we check that later, and it's on success, it's writing to that HTTP response writer. Now, the JSON package and the templating package don't know anything about the HTTP package. This interaction is mediated by an interface. This is, again, nothing new. In Java, it might be output stream, right? In Go, this is an interface called IOWriter. Again, an interface is just a set of methods, and IOWriter it's a set of containing a single method write, which takes a slice of bytes, and it returns the number of bytes written and an error. And so this HTTP response writer type implements that interface, and that's how this all gets joined together. All right, finally, to actually render those results, this should be pretty familiar to those of you who've used HTML templates. We can range over the results, produce a HTTP list item for each one with the title and URL, and then print out the results in elapsed time. And you can see a rendering below. All right. That's it for the search handler. That was, frankly, just the get introduces to Go syntax. Next, I'll go on to the fun stuff. In this case, I just want to say that everything I've done so far, the packages are just from the standard library. The standard library is very good. We build Google production software on top of this, and we make it available free to the world. So use it. It's excellent. The other thing to mention is that search handler was just straight line code, top to bottom. Everything it did, there were no callbacks, right? There were no futures. And this is where you can really get into the power of Go. Go gives you very, very lightweight threading and a very efficient runtime for swapping out and scheduling those lightweight threads. We call these threads goroutines, and Go servers can scale very well. We run each request in its own goroutine. So you can have hundreds of thousands of these things running, and when they block, they don't use an OS thread, so you're scaling very well. So let's talk in more depth about how Go's concurrency works. Go's concurrency is inspired by CSP, Communicating Sequential Processes, introduced by Tony Hoare in 1978. CSP states that concurrent programs are structured as independent processes that execute sequentially and communicate by passing messages. Sequential execution is fantastic. I know threads get a bad rap, but when you have them and they're light and they work, there's nothing better than having a stack trace to understand what your program is doing and being able to read code straight down and have that work. Async callback spaghetti is not your friend. It kills your diagnostics. It's very hard to understand. You're essentially taking everything your stack would have given you and wrapping it up into objects and passing them around. So Go brings back the sanity, and we'll go into a deep example to show you that. Go is built on three primitives. Go's concurrency: goroutines, channels, and the select statement. Goroutines are lightweight threads managed by the Go runtime. So Go is an end-to-end threading model, which means you can have hundreds of thousands, if not millions, of goroutines running on a very modest number of OS threads. And you just tell your Go programming how many OS threads to run, and it schedules the goroutines onto those. And a blocked goroutine doesn't consume a thread, right? So goroutines start with very tiny stacks. I think the default right now is a 2 kilobyte stack, and they grow dynamically as needed. So you don't worry about sizing your stacks. You don't worry about hitting your limit. And the syntax for starting a goroutine is very simple. Instead of saying f of args to run the function f, you say go f of args. And that starts it in running a new goroutine. And the code that executed that go statement just continues executing immediately. Now, it's not enough to have these lightweight threads. They need to be able to synchronize and coordinate. And this is where channels come in. Remember from CSP, independently executing processes that communicate by passing messages. In Go, channels provide that primitive. And you can think of them like typed synchronized queues. Okay? So if I make a channel of string, that means that I can pass strings around on that channel. So from one goroutine, I can send the string using this arrow operator. So here I'm sending the string hello on the channel named C. And so channels are also just values in Go. You can even pass channels around, and that's useful for certain design patterns. From another goroutine, I can receive from C. So here the arrow's on the other side. And that I'll receive that string S, and I can print that out, and that's that same hello string. So you can pass around strings, you can pass around maps, you can pass around pointers, right? You can pass around the memory you're sharing, right? So this gives you a way to safely share memory because you're essentially transferring ownership between distinct threads of execution. Channel communication is synchronous. A send operation will block until another goroutine is ready to receive, and a receive operation will block until a send can happen. Okay, so it's also a synchronization point. It's a very powerful primitive. You can loosen that synchronization by adding a buffer to the channel, and I'll show you an example of that later. Finally, there's the select statement. The select statement is a way for goroutines to block on multiple communication events. It's a lot like the select call in Unix. It looks like a switch statement. So here we have two cases. The first case, we're waiting to receive a value from the channel called in. In the second case, we're waiting to send a value, v, on a channel called out. This statement will block until one of the two cases can proceed. So if the in case is selected, if that happens, then that value will be stored in this local variable x, and we'll print it out. If the out case happens, we'll print out the fact that we sent that value. And only the selected case runs. The other one is guaranteed not to have run. If they both happen to be ready, then we choose a case randomly. All right, so those are our primitives. Let's see how we put them together to solve an interesting problem. You remember that in our search handler, we called that Google search function. We handed it a query, and it gave us some results. But that seems kind of simple, but what does Google really do? Well, given a query, we return a page of some search results and some ads. But we get those search results by querying a bunch of different repositories: web search, image search, YouTube, maps, news, and so on. Then we mix them and order them to produce what we think is the best result customized for the user. All right? So how would we actually implement this in our little server if we wanted to query these backends and assemble those results? So we're not going to build Google here, but I'm going to fake it out for you. We'll start with a fake framework where we're going to simulate 3 backends, each with a random timeout from 0 to 100 milliseconds. So we've got 3 declared here: web, image, and video. Each one we're constructing with this fake search function, right? And that fake search takes 3 parameters: the kind of search, web, image, or video, and a fake result, a title, and a URL, okay? And this fake search function, here's the 3 parameters: kind, title, and URL, all strings. It returns a search func. Search func is just a type I declared here. It is itself a function from queries to results. So how do we specify it here? We can specify a function inline with a literal, and this is a closure. It's closing over these kind, title, and URL arguments. So what this function is going to do is it's going to sleep from a random duration for up to 100 milliseconds, and then it's going to return a result. With the title, it's just going to tell us the kind and the query and the query and the title, and then the URL is the second element of that result. So that's our fake. And let's test that out real quick. Here's just a little test driver program. We're not going to run the server. It's just going to time how long this takes and print out the results, the elapsed time, and the error. So we run this. We get our web, image, and video results in 256 milliseconds, nil, which means no error. If we run that repeatedly, we get the same results in a slightly different time. And if we run this a few times, we'll notice that this total elapsed time hovers around 150 milliseconds. And why is that? Well, we're taking 3 random samples from 0 to 100 milliseconds, and we're adding them up. And the reason we're adding them up is that our implementation is serial. Our search function is taking the query to return a slice of results. And so here's our implementation. We're going to declare our result slice here again using a literal. Web is going to execute first, then image, then video, and then we return our results. So when we run that, we're adding up three things that are going to average around 50 milliseconds. And so we expect anywhere from 0 to 300 milliseconds, averaging around 150. That's our baseline. So this is Go, though. We can parallelize this. So let's see how we do that. We want to run the web, image, and video queries concurrently. So we're going to run each one in its own Go routine, and we're going to collect the results on a channel. So we declare this channel C as a channel of results. And we're going to start 3 Go routines, go, go, go. And each Go routine is going to run one of the searches and send the results on the channel C. Now, you'll notice here, I said earlier that you just say go and then a function call. Well, here I'm declaring the function in line as a closure with no arguments, and then I'm calling it with no arguments. So closures turned out to be a fantastic mate with Go's concurrency model because it means you can bind synchronous calls like this web search call to a channel in just a one-line simple expression. So that really couples quite well. And it means that the signature of web is just a simple synchronous function. It just blocks and returns a result. And here we're executing it in a concurrent context. And when we return, we're going to return a slice of 3 results. And those results are 3 receives from the channel. We want to receive 1, then 2, then 3. So let's run that and see what we get. All right, so first thing, here's our 3 results. The order changed, right? We got image, then web, then video. Well, what order is this? This is ordered fastest first. So image took the shortest amount of time, so we received it first, then web, then video. And it turned out none of them took longer than 15 milliseconds. So we got lucky there. If we run this a few more times, there's 45 milliseconds. You can see the order is shuffling each time. And you can see we're staying at or below 100 milliseconds. And the reason why is because the slowest one is only ever going to take 100 milliseconds. So that's as long as we're going to take because we're running them in parallel. So let's look at the last slide and this slide again. Here's the last slide, web, image, video. Here's the parallel slide, web, image, video. It's barely longer, if longer at all. And I could have cheated and made some of them more one-liners. So Go's syntax for doing this sort of concurrency is very lightweight. This is very powerful. But we can do better. Now, at Google, we care a lot about speed. So we've decided that 100 milliseconds is just too long. People are noticing. We've got to go faster. So we're going to have a new version of this search that takes a timeout. The timeout is another parameter, time duration. And we're saying that we don't want to wait any longer than 80 milliseconds. So we're going to call search timeout with an 80 millisecond timeout. And so we want this function to return at 80 milliseconds. So we can't wait for the slowest guys if they take longer. Most of the code is the same. We start a timer right at the beginning of the function. And this time.after function, it returns a channel. Right? It returns a channel. We saved it in this variable timer. And that channel, the time package is going to send a value on that channel after the timeout elapses. Now why? Why do we do it this way? Well, we need to receive the results from this channel C. But while we're waiting for the results, we also need to be checking that the timeout hasn't expired yet. We could just try pulling the timer in between receiving results, but then we might exceed our deadline if one of them is really slow. We need to wait for both simultaneously, and here's where select comes into play. So I've rewritten this as a loop. Each time through the loop, we're going to select on either we receive a result from the channel, in which case we append it to our vector of results, or the timer fired, in which case we're going to return an error timed out. In this case, I'm also returning the results just so you can see the subset of results we received. Typically, though, you wouldn't bother returning anything here because the call failed. If we get through this loop, we received all 3 of our results, we're complete, and we return the results and no error. So let's see how that works. Okay, here. It took 82 milliseconds. We got image and web, and we did not get video. And we got this error message timed out. Right? So let's run that a few more times. 62 milliseconds, all 3 results. 85 milliseconds, timed out. 85 milliseconds, timed out. Right? So we're timing out quite frequently here. When we take those 3 random samples, there's still a fair likelihood that one of them is over that 80. So this is a problem. Our users are complaining. So how do we avoid timeout? How do we avoid discarding results from slow servers? Well, what we do is we throw money at the problem. Let's replicate our search backends, And so we'll send our query to multiple web backends, multiple image backends, and multiple video backends, and take the first one from each of those repository replicas. So let's define a little helper function. I've called it first. First takes any number of replicas. This ... syntax is Go syntax for a variadic number of arguments. And it's just available to the function as a slice. You can index it and range over it the same way you would any other slice. So first is going to take a list of search functions, and return a search function. The function it returns is going to create a channel of results. It's going to create a little closure here to run the ith replica and send its result on that channel. And it's going to start a go routine for each replica. And then it's going to return the first thing it gets from that channel. Done. But there is a subtlety here. When I return, those other go routines are still running. Returning doesn't make them stop or anything. They still go. So how do we deal with the fact that they still want to send the results on the channel, but we've walked away? Here's where that channel buffer comes into play. What I've specified here is that this channel can absorb up to the number of replicas sends on the channel without blocking. And so this means that our other go routines are going to keep running. They'll send on that channel. They'll absorb, the channel will absorb the writes. Then everything will exit and clean up. So let's see an example of how to use this. I'm going to call first with two fake searches, replica 1 and replica 2. So here we got replica 1 in 54 milliseconds. There's replica 2 in 37. If I run this a few times, we should see it roughly balanced. We should also see that the average should be a little below that 50 milliseconds because we're taking the smaller of two random samples, right? Okay, so that's our first function. Let's put it together with our search function. So here's search replicated. We're going to declare replicated web to be the first of web 1 and web 2. Same with image, same with video. And then we just replace web with replicated web here, and image and video. So we run that. So here we got all three results. We got the web 1 result, the image 1 result, and the video 2 result in 64 milliseconds. And if we run this a few times, hopefully, so we can still get a timeout. In this case, web timed out, and this means that both web 1 and web 2 took longer than 80 milliseconds. So it's still a possibility. And we can make other trade-offs to try and speed that up, right? But we've greatly reduced the frequency that timeouts are happening. We've dealt with our tail latency. Another thing I want you to notice, the signature of search replicated here, this is synchronous, right? It's just a function call. It takes arguments, it blocks, it returns the results. The signature of replicated web takes an argument, returns a result. There's nothing about channels or callbacks or futures in the signatures here. The code and the interfaces are simple. All of the use of concurrency is encapsulated within these functions. This is one of the critical powers of Go, is that you can have simple code that does very sophisticated concurrency. So what just happened? We took a slow, sequential, failure-sensitive implementation of search, and with fairly straightforward transformations, made it fast, parallel, concurrent, replicated, and robust. No locks, no condition variables, no futures, and no callbacks. Now, obviously, we're using channels, and we're using select and go, but that's built into the language for exactly this reason. We believe these are the concurrency primitives that let you compose programs that do real work real well. All right. So hopefully, I've whet your appetite for Go. Hopefully, I've gotten you interested in the language, and you want to do more. Where do you get started? Start with the Go tour online, tour.golang.org. It is an online tour in your browser that walks you through the language from the basic syntax through to concurrency. Then, if you want to learn more, go to the Learn Wiki page. It has hundreds of resources that will take you as deep as you want to go. Now, if you're still interested, I want to talk to you about an important technique that we've discovered while trying to get a programming language adopted both within Google and outside, and it's running a pilot project. So as manager of the team, and as I've worked over the last several years really to get teams within Google and outside Google to adopt Go, I've had to understand what their problems are when facing with this. As I said, Google's an enterprise. We have a huge legacy code base. It's not just adopting any new technology, language or not, is expensive and difficult. And people are skeptical. You want to moderate the costs and the risks of switching to any new technology. And this is where pilot projects come in. I realize many of you probably already know this, but let's just go over it. You want to help your organization discover the benefits of your technology while moderating the risks. So step one, choose something small to write in Go. A service, a server, or a microservice, a tool, command line tool. You can either be a rewrite or something new, but something moderate that you can do with a partner. Find a friend and build a prototype. And you want to use this experience to find, well, are the libraries you need available? How do you integrate with the editors and IDEs your organization is using? How do you integrate with your build and test and deploy cycle? And you want to spend some time with your program. How are you debugging it? How are you profiling and optimizing it? And then compare, with a fair amount of skepticism, Go to what you're using today. Try your best to have isolated just the language change and keeping everything else equal. To the extent possible, make this an A/B change. I realize it's not 100% possible, but that's the goal. And then present the results to your team and your organization and discuss. We believe this is probably the fairest way to evaluate whether this is really buying you anything. I hope in my presentation I've shown you that it's a powerful language. I think if you think through the example I just showed you and the languages used today, you'll see that it's quite a bit harder in most languages to get that sort of behavior. We found this to be very powerful at Google. A final mention, since I've got a little bit of time. Go is designed for tooling. This was in the language design from the outset. It's a simple syntax. It's very easy to parse, and it's very easy to manipulate mechanically. So one thing about Go is that the formatting is standardized by a tool called GoFont. Everyone uses GoFont, and this means that machine-generated code and human-written code are indistinguishable. So this is hugely valuable, right? Because you can automate a lot of the maintenance of your code base. Editors and IDEs, there's existing integration for all the big ones. Eclipse, IntelliJ, Visual Studio, Sublime, Emacs, Vim, they're all in wide views. Let me show you the Go playground real fast, play.golang.org. You know, this is an online playground for Go. It'll compile and execute your code. And this turns out to be really useful for reporting bugs, for exchanging ideas, getting to know the language. And this lets me show you a couple more tools. So I mentioned GoFont, right? So if I have badly formatted code, I can just run format, and it'll do the right thing. And this is integrated with all your editors and IDEs already. And if I want to do, let me see, can I use log? I can run Go format. So what I did right there is I said run Go imports. And so it recognized that I'm using the log package instead of the fump package, and it removed the fump import and it added the log import. So this is another way that Go integrates with workspace really nicely. You just write your code, you save your buffer, it gets formatted, and the imports get updated. And you move on with your life. It's fantastic. If you want to share the snippet, you hit share, you get a URL to share with your friends. So this turns out to be a nice little helper when you're getting to know the language and when you're reporting issues. There's, of course, automatic completion, we have the Go tool for automatically fetching and building your code. It helps you manage your workspace and deal with remote packages. And then we have a cool tool called Guru, which does all of our static analysis. It gives you bug finding, it gives you code navigation, and this has various editor integrations as well. Finally, there's godoc.org. This is an index of all the generated generated documentation for open source Go packages on GitHub and in other repositories. So we can search for RPC and find. My internet connection's not great. We can find a bunch of RPC packages. Here's gRPC, which is the Google gRPC packages based on our internal Stubby implementation. It's available in 10 languages, and it's how we are talking to Google Cloud Services. We have a really nice API in Go. So this is familiar from Javadoc or PyDoc, but it's available as well in Go, and it's a great way to find the libraries you need. All right. So again, take the tour online. Check out the Learn Wiki page. And if you are into contributing to open source communities, you are most welcome. We have a great community for Go. Check out golang.org/project and get started there. Thank you very much.
So at this point, I'm seeing little gophers flying on rainbows, and I'm ready. I'm drinking the Kool-Aid. But I would wonder, what clues would I look for to know that Go is not the right tool for the job?
Excellent question. Wow. The guy who's going to present on Rust tomorrow is probably a better one to ask. So what we've really run into with fundamentally teams that run into friction. So I actually spent a lot of time thinking about this internally at Google, because one of the things I have to do in prioritizing what the Go team does is we go to our users and say, what are your pain points? What's keeping you from being successful with Go? Part of it has been internally a lot of the work in library completeness and efficiency. So I think Go has an excellent standard library that's very complete, and obviously we can build nice software there. Internally, people are pushing on Go very hard in very high performance, high throughput applications. We have a lot of optimization work to do. So there's a question of how hard are you going to push and is what's available publicly, does it meet your needs, your performance and scaling and cost needs? So that's one thing where a prototype always helps. It gives you something to measure. And also just finding the libraries you need. You want to make sure that if you need to integrate with particular protocols or particular templating systems or particular, you need to find the touch points of your system. Your operations team will have a strong opinion here. They are going to want to see a particular production contact surface for your program. You want to make sure that you can provide that. So that was a lot of our initial work on Go inside Google, was providing a production contact surface that looked just like the ones that C++ and Java had, so that our SRE teams became very comfortable with it. So that's the sort of thing that I think that pilot project can really help you. You need to explore this, and so that's one of the main things. I think, so I showed you on the slide earlier that Go, we think, presses up in that developer productivity axis, and we spent a lot of our time on the team pushing it sideways on that efficiency axis. But we're still not going to claim we're as efficient as C++ or C yet, right? We want to close that gap, but that's another thing that you need to ask yourself. If you're currently using C or C++ because you need every inch of performance, well, you'll have to measure, does Go meet your needs? But if you're currently, but if you're doing with anything less, I think Go actually can meet most performance needs, and it does particularly well in distributed systems where you really are managing a lot of I/O. Yes.
Hi, Samir. Quick question for you. I know you mentioned that there's no one IDE for Go.
Yes.
And I've been using Go Sublime for a long time, and I'm quite happy with that. But from my standpoint, all the languages I've used, C++, Java, and arguably Python, they've all gone through a period of time where one or two IDEs dominated. And I feel like that helped them spread out and make them more popular. I was wondering if your team is actively working with anyone for this one such IDE.
So we're certainly collaborating with these various external companies. So I think the IntelliJ company, and we talked when they started doing their integration. I can't talk specifically about what the Go team is working on. I can say that our general philosophy is to provide tools that can integrate into other development environments and encourage them there. So that doesn't really answer your question. Yes.
I'm just curious, the CSP paper initially appeared in 1978. Was there like a key technical innovation that occurred recently that allowed this to become a more mainstream construct, or is it kind of a case of unearthing a hidden gem that was sort of lost for time?
These ideas, you're exactly right, these ideas are very old. They have appeared recently. The Erlang and the actor model and Scala's actor model, darts, I think are all reflections of the same CSP model. Go is distinguished a bit by some of Rob Pike's earlier work with channels as first-class values. So in, say, Erlang, you're going to talk to other actors based on, I think, an address for their mailbox, whereas in Go, you're going to pass these channel values around, and that's your synchronization point. It's a subtle distinction, but it allows for different idioms and design patterns. I think these languages have been very old. The ideas behind CSP have been very old, but the need for them has become more keen lately. So if you saw the architecture talk this morning, Mohammed's talk, he talked a lot about the need to take advantage of multi-cores. And I feel like we now, the everyday developers, are feeling that pinch, the need to really take advantage of multi-cores. But we don't want to convert all of our algorithms to parallel algorithms or to vectorized stuff. And what I showed you here is that we could take something where we just have synchronous functions, we just want to run them in parallel and just sort of spread them out and then gather the results. And that, I think, is a lot easier to wrap your head around. And so I think that's one thing that distinguishes this approach from what you've seen before. In many ways, that bit of syntax is sort of incremental over what you've seen before, but it's the whole runtime underneath it that makes it efficient that's the big jump, right? But Haskell, Erlang, Scala, they all have various kinds of concurrency built in as well. So there's a long lineage. Robert Griesemer had a great talk at last year's GopherCon on Go's lineage. And if you're interested in the history there, that's a great one to check out.
Other mic, switch.
Oh,
Other mic.
Hi, I would have expected better performance on your first curve in terms of why is it similar to Java, given that it's lighter weight and has pointers and is direct native code?
That's a good question. Java is about, what, 20 years older. It has a lot of work on the JIT compiler and garbage collector that I think have made it. I think otherwise Java probably would have been over here, right? And so I think Java has pushed itself rightward quite a bit over 20 years. And so Go, I think, is starting comparable to Java, but we can push rightward from here.
Okay, thanks.
Yeah, Go is only 6 years old at this point.
Okay, thanks.
Hi, and just got to say, I love your quote about code should be written to be read. So, mine was talking about the pointers a little bit more, and why in Go that was something you decided, and just a little bit more information about that. You kind of talked about it and moved on. So
yes, I actually thought I was going to be very tight on time with this talk, so I must have been going fast. So pointers fundamentally allow you to distinguish between inline values and indirection, right? So in Go, you can actually lay out a flat struct that has nested structure that is entirely linear in memory, right? But a pointer is literally one in direction. So if you want control over that, and if you want control over memory locality, Go gives that to you. So I think that's the critical difference. And that if you want a reference, that's where you pull in a pointer. But if you want to just lay out flat memory so you have that efficiency of access, you just lay out a struct or an array or whatever.
So I've had a chance to play around with Go, and I've been following along with it for quite a few years, finally at least getting the proverbial feet wet, as it were, between picking up on some projects and also developing on my own. And one of the things that I have noticed as more of a trend is more of the transition away from using Go as a dedicated compiler to more like a full-featured build suite, as it were, where you're using it for retrieving packages, or at least
the Go tool
libraries.
Yes.
Right.
Okay.
So one of the things that I had noticed, especially futzing around with Kubernetes, is that the dependency mechanism for trying to automatically bring in the packages that you need without having to check them in as well still seems to be more hit and miss.
I think it's probably too simplistic for most real-world use cases. Like, it's great for getting started in rapid prototyping, but I was just talking to someone earlier today, the name escapes me at the moment, that package management and dependency management is certainly an area that we need to actively develop. There's been some work in the last 2 releases to provide better support in the Go tool for vendoring, but I think there's a lot on dependency management and package management that needs improvement.
Yeah.
And I think this is just a maturity issue. I think it's also partly a reflection that the Go team works inside of Google that simply doesn't have this problem. And so we are not the ones best suited to design the solution.
Yeah,
right?
Trust me, the go-get aspect has come in real handy, but being able to at least record that kind of list and using something like GoDep, which may or may not look into the vendor library,
right,
or at least refer to where you're supposed to point to.
I think there's room for organizing the community effort around package and dependency management to help standardize and get something decided, because I think that will allow everyone to move forward. It's something we need to do.
Okay.
Thank you.
Hey, thanks for the talk.
Yeah.
So the Go channels seem a bit like green threads.
The Go routines.
Go
yes,
routines, yeah.
very much.
Do you have to worry about managing like Go routine pools for efficiency, or not really?
You don't have to manage explicit pools unless, so what was the talk we saw earlier? The Hootsuite talk that was talking about managing, how much memory you want to use in sort of concurrent. So you can certainly create a pool of Go routines. You can start, say, n Go routines and have them all receiving from the same channel. So channels are synchronized, they're safe to be received by multiple Go routines. So for example, say you are reading files off a file system, you want to process files in parallel. If you just iterate over your file system, say you want to run the MD5 sum on every file in a directory. If you just iterate over your file system and start a Go routine for each one, you could easily pull in more memory than you have on your machine by reading the files into memory, right? So you may want to bound that. Now you could bound that with a semaphore, or you could just bound the number of Go routines that are doing reading. So you start a pool of Go routines and you feed them files over a channel. So Go makes it very easy to construct that sort of restriction. So it's not about controlling the pool or controlling the runtime fundamentally. It's more about just controlling how the data is flowing through your system. And I think that resource management is a tricky problem. I think in many cases, what you really want is a semaphore that models your resources. and use that rather than a pool. Because creating and killing go routines is lightweight enough that it's fine to just do it all the time. Yeah.
That's my main.
Yeah, it's very light. Yeah, I haven't noticed anyone that being a particular performance problem, because we start a new go routine on every RPC. Like every RPC handler in the server, we start a new go routine. So we're serving thousands of QPS. That's fine. Yeah. Thank you all very much. Oh, one more. Yes, sir.
Yeah, hopefully I'll make this quick.
Yeah.
So I actually have done a little Go programming and have kind of moved away from the language just a little while ago. And one of the reasons that I was in that scenario was basically that, and I actually noticed it was missing from the list, and this could just be that I don't know enough about the language. But you'd said something about diagnostics, and I was wondering, on the list, considering that Go changes the runtime model, I thought it was very conspicuous that a debugger wasn't on the list. And is that something that...
Yeah.
So,
So there is a Go debugger called Delve that's been developed by an external party, and it's been maturing nicely. There's also a number of built-in diagnostics in the runtime. So there's a CPU profiler, there's a heap profiler. We have nascent support for heap dumps that we're working on, and heap inspection. And then there's this really cool thing called the execution tracer. The execution tracer, if you're familiar with, I think it's Haskell Threadscape, where it shows you how the Haskell sparks are executing on the CPUs. This is something very similar for Go, where you can actually see a trace of which CPUs your Go routines executed on, which functions they're executing, how they were blocked on channel operations or mutexes and so on. So we have diagnostics both for the gross level, you know, where's my memory being allocated from and where's my program spending its time, to the very fine grain. Yeah.
thank you.
Sure. All right.
Thank you very much, Samir. There's a 20-minute break now. Coffee will be available in the room across the way. The last session of the day is a joint session, which will be upstairs. So Brandon and Greg will be talking about performance analysis. So hope to see you up there.